inviting me to this wonderful workshop and beautiful country. So today I'm going to speak about quantum trajectories, interaction, and page curve entanglement. So the talk is going to be basically divided into two parts. So in the first part, I'll talk about page curve entanglement dynamics with quantum trajectories, and that work is available here. This work was done with Katha Ganguly, Preeti, Atharva, and Vijay. And in part two, I'll speak about page curve entanglement in interacting quantum systems. Of course, my work is now easier because Abhishek introduced most of the important concepts and so on. And so I'll just start with the general platform. So we are basically interested in considering a quantum system that is coupled to an environment. This environment can be infinite in principle or much larger than the quantum system. And a couple of questions naturally come to mind. What is the number of particles that leave the system as a function of time? Let's say you sort of load the quantum system with some particles and you just ask what is the number of particles that leave as a function of time, or what are the number of particles that enter the vacuum as a function of time. What about density profiles, currents, number fluctuations, full counting statistics, and so on. How long does it take to empty a quantum system? What about entanglement entropy between system and its complement? Is there some sort of collective theory that captures some of these essential features? And is there some connection between entanglement entropy and Boltzmann entropy? And if you have noise or stochastic processes in the quantum system, or some measurement based processes in the quantum system, or some interactions in the quantum system, how do these kind of quantities change? So that is sort of some set of broad questions that come to anyone's mind. So I'm not going to repeat this. This is something that Abhishek already discussed. So when you have a system basically coupled to a large environment, it sort of is reminiscent of black holes. So basically entanglement between black holes and radiation starting from an unentangled initial state of just the black hole. So is the same thing that Abhishek mentioned, that if you black hole radius, the effective Hilbert space dimension increases, and then at some point there will be a peak in the entanglement entropy, after which the entanglement has to decrease. So that is the rough setup. So irrespective of this relation with black holes and so on, basically the idea is you have a system, a quantum system that's coupled to a vacuum, and you want to study entanglement between the system and the vacuum. And most studies, when they study entanglement, they are used to bipartition setups, where you have system and its complement, both are bipartition. But here the complement is much larger than the systems. Okay, so the non-interacting case was discussed in detail by Abhishek. So now we are going to ask, what happens if your system is either fully interacting or it's subject to some stochastic processes? So basically, and what are the kind of things that you can say? So of course, if you have bilinear Hamiltonians, things are somewhat easier. You can calculate the correlation matrix in this form. All initial conditions go into C0 here, and from the correlation matrix, you can basically extract the density and let's say the current between the system and the bath. And if you have Gaussian initial states, you can compute Wien-Neumann entanglement entropy from the correlation matrices. They are related to eigenvalue of correlation matrices, or particle number of fluctuations in the system. So imagine you have a system that is filled, and what is the number of fluctuations of total number of particles in the system, or what is the number of fluctuations of total number of particles in the bath. So you can sort of compute these kind of things, and you can ask questions whether there is some relation between all these things, whether entropy and current, or density and entropy, or number of particles in the system and entropy? Is there some sort of trend or some sort of connection? Okay, so okay, so now let me start with part A. So basically we have two kinds of systems. So we are asking what is the impact of stochastic probes on, say, von Neumann entanglement entropy, or is there some universality properties in terms of temporal growth, system size, scaling, etc. So the system is the following. This is my system and this is my bath, and in addition to sort of a non-interacting setup here, it is subject to probes. So in the first part of my talk, I don't have direct interactions, that will be the second part of my talk, but it's subject to some noisy processes. And there's another geometry where even the bath is subject to noisy processes, and so we call this probe and probe clean. So now the question is, what happens to various quantities? Is the setup clear? Any questions? Okay. So now, so what do I mean by stochastic probes, right? So by stochastic probes, I'll just talk about two kinds of stochastic probes. You can also call them quantum trajectories. So the first thing is stochastic unitary processes. So this is essentially similar to the model that Abhishek spoke about, but the difference being that you can have on-site fluctuating space-time noise added to the Hamiltonian. So the evolution is stochastic and but unitary. So this is stochastic unitary process. Okay. So there's another stochastic process which goes with the name of quantum state diffusion. This is a situation where the system is prone to weak measurements. So you're continuously doing weak measurements on the system. You can sort of map it in terms of quantum trajectories, and then you can ask in such a system what happens to entanglement between the system and the reservoir. Okay, so just two stochastic processes, and we are going to ask about these kind of questions. What happens to page value, page time, number of fermions radiated into the reservoir, relation between rate of entropy production and current, and so on. Okay. So now let me just discuss these two stochastic processes. So the first stochastic process is called stochastic unitary process. So this is my setup. So these are two different geometries, but you can just focus on one of the geometries where only the system is subject to noise. Okay, the bath is just a clean tight binding model. So under this stochastic process, the lattice is subject to on-site fluctuating Gaussian noise. So you just have on-site noise, and this is space-time white noise, and the Schrödinger equation becomes a stochastic Schrödinger equation. This is what we call quantum trajectory, and you can write the evolution of the wave function, a pure state, as in this form. And since this is a pure state evolution, you can ask what is von Neumann entanglement entropy and so on. So once you have this pure state, you can calculate this correlation matrix per trajectory, and then from there you can calculate entanglement entropy per trajectory, and then you can do ensemble average entanglement entropy. So you can do an ensemble average over all trajectories. So this is the so basically you do a stochastic evolution of pure states. Okay. So now so in this case, what happens is that you can write this quantum trajectory in some convenient form. You can write it in this form here, where L is the total size and so on. But the idea here is that you can write it in as a L cross LS matrix, and then from this matrix, which depends on time, you can build your correlation matrix per trajectory. Okay, so and from this correlation matrix, you can compute various quantities, including entanglement entropy per trajectory. You can also compute number of fermions leaking out of the system and number of fermions the current between the system and the bath in that junction. Okay, and at the very end you can always perform average over trajectories. So this is the idea, and these are the two sort of geometries. Okay, so the next quantum trajectory description goes by the name quantum state diffusion. So here basically, recall that the previous trajectory was just Hamiltonian subject to space-time white noise, but here the stochastic dynamics under this protocol, it describes evolution of a quantum system that is subject to weak continuous measurements of local particle number. So basically, you can perform these measurements by coupling the system to a detector and making projective measurements on the detector. Okay, so basically what happens is that effectively the system is subject to weak continuous measurements, and so therefore you can imagine that if you weekly keep doing measurements on the system, whatever the entanglement is probably going to not be the same as the situation where there is no measurement. Right? So it's a different trajectory which captures different kinds of physics. So here also after some algebra you can basically write the quantum trajectory in terms of some M matrix and so on. But the important thing is, so basically this is the quantum trajectory, and you have a different U matrix. Notice that this quantum trajectory is, there is this n hat of t, so it is basically nonlinear. Okay, is nj hat of t. But once you do this, you can basically calculate again the correlation function and extract all the quantities from it. Okay, so is that is there any questions? Okay, yeah.
I guess it's important that all of these terms are like free fermion for.
Yeah. So the non-probe, non-stochastic part is non-interactive. Yeah. Okay, so now what are the so I'll go directly to the results. So let's focus on this geometry. It's not okay. So let's focus on this geometry, and this is the noise-based trajectory, and this is the measurement-based trajectory. So what we see in the Weinmann entanglement entropy is that you have a square root of t growth, and at the page time, and so the page time grows as ls square. The page time is the time at which you have maximal entanglement, and so in bipartisan systems you can calculate the system size dependence of the steady state entanglement, and here we basically characterize the page value, that is the value of the entanglement at the page time, and you see a volume law. So you see that this goes as volume law and this goes as square root of t. So right away it is different from the case where you have no noise. So if you have no noise, first of all the entanglement grows as t, okay, as Abhishek was showing, and it still has volume law, of course. Okay, so there's a complete difference in the growth of entanglement. In the QSD, the measurement-based thing, the growth of entanglement is log t. So this is okay. This is sort of expected because these are measurement-based protocols. So you think that the Weinmann entanglement has to reduce. So we see a clear log t behavior in the growth. Yeah.
So this is conserving U1, right?
Yes.
So I thought that free fermions with U1 conservation are always area law in their entanglement. Does this result from Mellon?
No, but this is with so this is with domain-1 initial conditions, right? So
but you're also doing these state diffusion measurements, right? Or
So this is, so you are talking about the measurement part.
Yeah.
Oh yeah, sorry. In the measurement part, it is not. It is eventually going to be area law.
Okay. Yeah.
That's right. So the noise part is volume law.
Exactly. Yep.
And this is eventually area law. Yeah.
And what about the bottom right? So what's going on there?
Bottom right is this one.
Yeah.
Yeah. So I'll come to this. So the bottom right is, so basically this is for a different geometry. Okay. So this is for a different geometry, and so in this geometry, so let me just explain this, and then so in this geometry, what happens is that the stochastic the noise process just gives you a root t, but here the measurement based process actually doesn't give you a log t. It seems to give a log t. But the page value with system size is again going to area law. So this is log t probably because, so in this case even the bath is subject to measurement. So this is log t. Okay, and I think even here the page value itself grows as ls square, the page time, where ls is the size of the system. Okay, so now we can ask, what about is there a connection between entropy, production rate, and current? So by entropy production rate I mean ds by dt, and current is basically current between the system and the bath. So in the noise protocol, we see very good evidence that ds by dt is proportional to current. So basically this means that, so ds by dt is basically proportional to current, but current is basically dnr by dt, where nr is the number of fermions that enter the bath. Okay, and this basically means that S is basically, the behavior of S and nr is same. Okay, so the entropy grows as root t, and nr also is supposed to grow as root t. So the number of fermions that enter from the system to the bath grows as square root t, which is sort of understandable if you think of an effective description of these stochastic processes in terms of Lindblad equation. Okay, so this is irrespective of the geometry. Of course, this will not hold for measurement-based protocols, because nr will still go as root t in measurement-based protocols, but S will go as log t. So the reason nr will go as root t is because nr will be the same whether you talk about stochastic noise processes or measurement-based processes. Okay, and this is because all these the two stochastic processes that I mentioned at an average level maps to Lindblad equation with dephasing. Okay, so is that clear? So basically I'll make a comment about the Lindblad equation only in an average sense. So you take any of those two stochastic processes, actually there are many other stochastic processes, which basically upon averaging can be described by this Lindblad equation with a dephasing term here. Okay, so but Lindblad equation basically gives mixed states, so it's not really suited for computing von Neumann entanglement entropy, so you don't really follow this route to study entanglement entropy. That is one point. But you can calculate many things that depend linearly on the density matrix. So if you calculate the average number of fermions exiting the system, it's going to be the same with Lindblad, with trajectories and everything. And same with current between the system and the bath. And so this Lindblad equation in particular actually is quite interesting. It has some very special features. So first thing is that for this Lindblad equation, the 2-point correlations close within themselves, even though you have little non-trivial terms here. But if you write equations of 2-point correlations, they close. So that is one thing. So you can do many things very accurately. So the point is, if you start with a system which is non-interacting, then you would expect ballistic behavior, okay, things will spread ballistically and so on, and most of the exponents that you will get are going to be reminding of ballistic exponents. But if you actually see the Lindblad with probes, if you don't have the probes, everything will become ballistic here. But as soon as you have a probe, basically you always get, most of the time you get diffusive behavior. So it basically is sort of thought of as mimicking scattering effects. And there are many works in that direction. And also it mimics environmental imperfections. So if you have a clean tight binding model which is inside a phonon substrate, then you can sort of mimic it by a tight binding model coupled to a dephasing Lindbladian. So this in itself is quite interesting, and there are a lot of exact results and so on and so forth by many people here. So that is the thing I wanted to mention. Okay, so I'll conclude with part A of the talk. So we examined the entanglement entropy page curve under different kinds of stochastic processes following the quantum trajectory approach. So depending on different trajectories, you can observe distinct time dynamics and growth and decay of entanglement and all. So yeah, we have some exponents of some intermediate decay exponents and also some long time decay exponents. And QSD protocol, due to local monitoring, always has slower entanglement entropy. And there is some relation between this entropy production rate and current. And of course the reason for this is, at the end of the day, at each trajectory level, it is very close to a non-interactive system where such things happen. So that is probably the underlying reason. But still, we are working on some ways to develop thorough understanding of our results. Here the main problem is we cannot use the Lindblad equation, because if you are interested in entanglement, it becomes a problem. So yeah, so basically analytical understanding is somewhat less, or almost, yeah, very less. So now I'll go to part B. Is there any question? Okay. So now I'll go completely to an interacting quantum system. So now there are no stochastic processes, no probes, and so on. And the system is the following. So the setup is the following. So we have a system with which is an x-axis spin chain with and without nearest neighbor interactions. So J prime is the integrity breaking term, and the bath is also an x-axis spin chain. Okay, so system and bath. So in this talk we'll focus on this. Bath is also interacting. It's an interacting bath. And there are some very relevant and interesting papers that I have put here. So our setup is the following. So in the part A of my talk, my initial setup was always a domain wall. So the fermions are fully filled. The system is fully filled, and the bath is fully empty. I should have mentioned that. And here we consider the bath is always vacuum. The bath is always empty. But the system is either fully filled or it's an infinite temperature half-filled state. So we have two initial conditions. And the system bath coupling is just itself like an XXZ model at the junction. Okay, so this is basically fermions in 1D with integrable and non-integrable interactions. So what are the basic quantities of interest? So one is the total magnetization dynamics in the system. So basically at any point of time, calculate the total magnetization that is lost from the system, or total magnetization that is gained by the bath. You can also compute variance of the total magnetization in the system or equivalently in the bath. So here you can compute von Neumann entanglement entropy, because the total state is a pure state, and then you just calculate von Neumann entanglement either this way or this way. And I'll explain a little bit more details about Boltzmann entropy because that was mentioned in Abhishek's talk. So these three are somewhat non-coarse grained. This is coarse grained. So basically, we have to define a coarse grained description of the full setup. And the macro state we consider here is one in which we divide the full setup into spatial cells, and the spatial cell is itself of size ls. Recall that ls is the size of the system, and so each bin is size ls. So if the system is size 10, the bin size is 10, and if bath is size 200, you have 20 bins. Okay, and in each bin we can specify the average number of particles or magnetization equivalently, or average energy. And then basically Boltzmann entropy counts the number of microstates that correspond to this given macro state, characterized by this average energy and average temperature. Okay, so what is the procedure? So you compute the state of the entire setup using T, BD and so on for all time T. And then using using this entire wave function, you compute the average energy and average magnetization in the system. So this is Boltzmann entropy for the system, and system itself is one whole bin. Okay. Then you basically find the grand canonical distribution, which is given by this, and this is system and this is also system, where you have to determine these two parameters beta and mu. But these two parameters can be determined numerically by requiring that this is satisfied. Okay, so you have to satisfy this and this. So this will help you determine beta of T, beta as a function of time and mu as a function of time. And once you know this, you can compute the Boltzmann entropy of the system, which is given here. And unlike von Neumann entropy, Boltzmann entropy can be different for the system and the bath. So what do we do for the bath? We do a similar procedure. We divide the bath into spatial bins where each bin has equal number of sides. So for each bin that belongs to the bath, you calculate the same thing. And this is the Hamiltonian of the bath. Here you see that Hamiltonian of the bin belonging to the bath. So you sort of ignore the coupling between bins. Okay? And then you follow similar procedure and find mu and beta for each bin that belongs to the bath as a function of time. And then you compute the total entropy of the bath as sum of total entropies of all the bits. Okay, so now that is the procedure for calculating Boltzmann entropy. Now let me go back to von Neumann entanglement entropy at very early times. So recall that we have two initial states for the system. One is a polarized state and another is infinite temperature state. So the initial state is always prepared in this way, and bath is always down, 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 down. So extremely early times, of course, you can even do a Taylor expansion. But you can actually get some results at very early times. So at very early times you can show, first for the polarized case, meaning the system is polarized, system is domain wall, that at very early times, at least up to this order, the only sides that are affected are two sides on the system side and two sides on the bath side. So you have effectively a 4-qubit system at very, very early times. And because you have this 4-qubit system, the rest of the system and the bath essentially don't talk at this order in time, and then you can show, you can basically calculate the von Neumann entropy, which basically goes as T square log T and so on. And you can calculate the number of fermions that enter the bath, which grows as T square, and variance of the bath also grows as T square. So this is for the polarized case. These are extremely early times. At these times, even the interactions don't matter. So they are not kicked in. You can show that also. Now for infinite temperature, actually it turns out that even calculating one-Neumann entropy for these extremely early times is somewhat not clear. So this is challenging even for infinite temperature. This is even challenging for very early times. But magnetization and variance you can compute. So basically, what is the initial condition of the setup? So the bath is always down, and the system is basically summation over Ck chi k, where Ck is basically complex number chosen from a distribution with mean 0 and variance half, and chi k are all sorts of product bases with zero magnetization. So that's your initial condition. But with this initial condition, you can basically calculate that number of fermions that enter the bath, which was initially empty, goes as T square by 8. And the variance also goes as T square by 8. So there is no result for one-Neumann entropy at the initial time. So, and the underlying reason is more or less that the system is not doesn't really reduce to effective four qubit system and so on. So that is okay. So that is so now we'll discuss the numerical results for that will capture very early time, intermediate time, and long times. Okay, so now recall that this is the setup. So this is the setup where the system can either be an integrable spin chain or spin chain with broken integrability. Bath is integrable in all cases and so on. So we use TEBD and it has been checked that the bond dimension, things converge with respect to bond dimension and so on. So typically the system size is 10 and bath size is 200. So we can probably go a little bit more, but basically it looks like in this regime we can capture many coefficients. So the problem with these kind of computations is that it's not bipartition. So really we need bath to be much larger than the system. So we can't really take a very large system. So we'll present 4 cases here. So the first case is integrable and polarized, and integrable and infinite temperature is the second case. Again, bath is always empty to begin with. And the second case is non-integrable and polarized, and non-integrable and infinite temperature. These are the any questions? Okay, so now let me focus on this case when it is domain wall initial condition, but integrable quantum spin chain. So let us focus on the right side of the plot first. So this is the density profiles. Okay, so this is the density profiles, and delta 0.8. So delta is this anisotropy. So delta is this anisotropy here, which basically is also here and here and so on. Okay. So the thing is, so this is the domain wall dynamics. So this finite domain wall basically evolves and so on and so forth. So you see that particles are sort of up to this part. So this is 10. Up to this part is the system, and 10 to 150 or even further is bath. So you see that there is domain wall evolution, but the domain wall is finite. So that is important here. So domain wall is finite. So what do we see? So first these are these extremely early times, which is sort of which exactly matches with the analytics and so on. But then there is this intermediate time. So let us focus on the entanglement entropy, which is this color, bluish, this color. So the growth of the entanglement entropy goes as 0.3. And in this case, and basically it goes as 0.3 in both cases, at the isotropic Heisenberg chain limit and even at easy plane limit. So it goes as 0.3, and this is reasonably trustable, because what we can do is we can keep on increasing the system size If you're interested in growth and not the page curve, then you can, increase the system size and not increase the bath size. And if you do that, this 0.3 seems to stay. So the exponent is 0.3. Yeah. So, but then after this, it goes through a page value and then drops down. And in this case, what we notice is that the page time basically, there is some evidence of how it scales with LS and how it goes down after crossing the page time. So one thing I wanted to mention here is that typically in literature you would see that when you have maximum entanglement, most of the time half of them have gone out from the system to the reservoir. But that is not at all the case. It can really vary. Even in the part A of my talk, when you have maximum entanglement, it can even happen that only 40% of the particles have gone out. So it's not so important how many have gone out, it's also what entanglement they carry. So, and here we have clear evidence. For example, the fraction escaped around the page time is 75%. So you need 75% of particles or spins to sort of go to have maximal entanglement. So it's not half, many times. So okay, so now we can compute the page, the average magnetization in the bath. So average magnetization. So we don't really understand many of these exponents because the average magnetization basically goes as 0.83 here, and in in isotropic limit it goes as 0.66. So here it somehow seems to be close to some KPZ exponent, but yeah. So this is like 2 by 3. But so this is how the average magnetization grows in the bath. And in non-interactive systems, there is a very important result that by and large the Weinmann entanglement entropy is very close to the second cumulant. Basically, it's an expansion in terms of all cumulants, but higher cumulants are very, very less. So usually Weinmann entropy is almost up to some coefficient proportional to second cumulant. So here obviously we wanted to know what happens here, and there seems to be no necessary relation between variance of this number density versus and Weinmann entanglement entropy. So here, so these are the exponents, and this is the fraction that is escaped around the page time for the isotropic case is about 55%. So this is the integrable case with domain wall. Okay. Any questions? Okay. So now I'll go to the same thing, but with initial condition in the system being infinite temperature. So if you have infinite temperature initial conditions in the system, then you have we get some other exponents, but I wanted to make this remark that one second. So that the growth of entanglement entropy is much higher when the system is prepared at infinite temperature. So this is 0.8, and this is also close to 0.8. So we don't see too much difference between easy plane and isotropic case, and so on. So this is the growth of entanglement entropy, and here you see that 45% have exited, and here 41% have exited the system at the page time. So here we again don't see any definitive relation between variance of Nz and entanglement entropy and so on. So these are the exponents that we are reporting here. So yeah. So this is what I wanted to say about, and this is how the density profile evolves and so on. Okay, so now we wanted to compare Boltzmann entropy with von Neumann entropy. So recall that Boltzmann entropy was calculated by the procedure I mentioned. So now for the integrable case, this is the comparison with system and bath Boltzmann entropy. So this is domain 1 and this is infinite temperature. So you see that. So let me start with domain 1. So this is easy plane and isotropic. So you see that there is this bath Boltzmann entropy which essentially follows the system Boltzmann entropy, and then bath Boltzmann entropy sort of departs and the system Boltzmann entropy comes down. And the system Boltzmann entropy, which is this red thing, is having a strong resemblance with the von Neumann entanglement entropy. Okay? And the same here in the isotropic case, the bath Boltzmann entropy departs, and but the system sort of follows the trend with the entanglement entropy, von Neumann entanglement entropy. One thing we see for sure, we have not found any violation of one thing, which is the system Boltzmann entropy is basically always higher than the von Neumann entanglement entropy. Even though the matching may not be good, at least it is higher. Okay, so and for the infinite temperature case, we see much better agreement. So you have this system, you have this bath Boltzmann entropy, which essentially follows the von Neumann entanglement entropy and then departs. Bath Boltzmann entropy always departs and basically is expected to, in the infinite, bath size limit is expected to keep on growing. It won't saturate. Okay. And here the system Boltzmann entropy basically is maximal because it's infinite temperature state. So it comes down and eventually crosses this bath Boltzmann entropy at phase time and then catches up with the von Neumann entanglement entropy. So this is the status of the comparison. So all these green plots remind you of this Hawking's entropy calculation of the reservoir entropy. This is just a resemblance. And the system, the von Neumann entanglement entropy is this orange curve here. And the system Boltzmann entropy can even come from here. But usually what happens is that it just catches up and then it agrees with the von Neumann entanglement entropy. So, any questions? Okay, so this is the numerical result for the integrable case. So now let me go to the non-integrable case. So non-integrable case, what happens is the following. So recall that this is the non-integrable case. J prime is set to 1. And this integrated breaking term is only in Sz. Okay, Sz I and Sz I plus 2. So for the domain 1 initial condition, what happens is that the domain 1 hardly evolves. Okay, the domain 1 hardly evolves. This almost resembles integrable XXZ spin chain in easy access regime. Okay, even there the domain 1 doesn't evolve. And basically what is happening is that this J prime is basically, I think, enhancing this effective delta and freezing it. So basically the domain 1 freezes. So if this domain 1 is freezing, there is not much to discuss because nothing is happening. So it just grows and saturates. And this we have also confirmed that the polarized initial state has basically a very high overlap with a single localized eigenstate of the entire setup. So if you take the entire system bath setup, you will see that it has very high overlap with one localized eigenstate, this domain 1. So this is of course not going to be true if you change the initial condition. So this is one of the examples where most of what I spoke in this talk is somewhat sensitive to the initial conditions of the entire setup. So the last result is infinite temperature with non-integrable case. Okay, so at least what we see is that basically infinite temperature, of course, things evolve and the domain 1 evolves and so on and so forth. But at least from the exponents reported here, there is not too much difference between integrable and non-integrable case here. Because I mean these exponents are not that different between integrable and non-integrable case, it would be nice to see some very big difference between integrable and non-integrable models in spin chains. But basically, yeah, basically this is, you can do all these things, all these early time calculations even for the non-integrable case, because as I said, interactions don't kick in, the delta terms don't kick in, so everything here is same. So, okay, so now I will end part B. So basically we studied quantum dynamics of von Neumann entanglement entropy of an interacting system with and without integrity breaking terms connected to a bath, and we computed the mean particle number and particle fluctuations as a function of time. We studied domain wall and infinite temperature initial conditions. So we are reasonably confident of all these exponents because we did some system size analysis. So we have some characterization of the page curve, and we also compared coarse grained Boltzmann entropy with fine grained entanglement entropy. So obvious question here is, it will be nice to have an understanding from hydrodynamics or generalized hydrodynamics of these kind of entropies for both integrable and non-integrable spin chains. Thanks.
There's some questions?
Yeah.
Yeah, please.
Even in the non-integrable case, the bath is still integrable, no?
Bath is still integrable, yeah.
Would that change? Like if you make that also non-integrable, then do you just get?
Yeah, so I think it's a bit hard to do that because to do MPS, because to break the integrity of the bath, we need next nearest neighbor interaction, and it becomes very hard to do MPS for such a long system with next nearest neighbor.
The physics will change, right?
But yeah, but with spin chains you never know. But yeah, probably exponents will change. But I wouldn't be surprised if it doesn't change also. So one thing we did, which I didn't report here, is when the bath is non-interacting. So when the bath is just XX, and there we see some changes which we can sort of explain. For example, the entanglement growth between system and bath is even higher. That's because if the bath is non-interacting system, particles can exit faster and so on. But we did not do the case you mentioned. But that's hard. We wanted to do that, but we did not. Yeah.
And the relation between, you said there was some relation between the second cumulant, which is the 2-point function, with the entropy.
Yeah.
Is that like, does that come from some kind of intuition, or is it like?
No, I think so. This is for non-interacting systems.
Oh.
It's for non-interacting systems, and it's a very rigorous result.
Oh, it's for just non-interacting.
Yeah, it's just for non-interacting systems. So, yeah, so that's why we certainly don't see it in interacting systems. We see it in that first part of my talk for trajectories, but that's because at the trajectory level they are still non-interacting. So, yeah. Yeah.
Can you say again, like, how do you compute the entropy? So you take a system, you split it up into small parts.
Yeah.
And then how do you compute the entropy of the small parts?
No. So what we do is the following. So we cut the entire setup into bins. Okay. So and for each bin we calculate the average energy, and average magnetization. Okay. After finding the psi of t, this we do numerically, and then you calculate this, and then you ask what kind of grand canonical distribution would give you this answer. So you have to fit beta and mu, and then.
But so this is an integrable, like, spin chain, right?
Yes.
So in principle, like your state in like this location is not given by like this quantum canonical ensemble, but by some GTE.
Yes.
To measure like all of these kinds of quantum.
Yes. So yeah. So obviously there is no reason to cut it off at this stage, right? And probably that will improve maybe the relation between Boltzmann entropy and von Neumann entanglement entropy. But yeah, that's a hard problem. Yeah.
I mean, if you tried just you chop your system up into bits and just compute the von Neumann entropy of each, reduced density matrix, just add them all up to get the Boltzmann entropy, that seems like it would work.
You calculate the von Neumann entropy between
Of each bin.
Yeah.
Because now that's a subsystem, and it seems like you should add them all up and get the Boltzmann entropy by ETH.
Okay.
Would try that at some point numerically. It does work pretty well.
Yeah.
But you calculate the von Neumann entropy between a bin and the rest of the bins, or
And the rest of the world, yeah.
rest of the world?
You compute the reduced density matrix, and then compute its von Neumann entropy, assuming that it's thermal, which it probably is with ETH.
Okay.
So yeah, I guess Ramar remembers this better than I do, but
I mean, I just know that
Yeah.
I tried that get condition
Yeah.
in different contexts at some point, and it works
Yeah.
reasonably well.
Okay.
I can tell you about.
Okay.
also have you tried doing, so it seems like one could compute something like the purity, if you took a random U1 conserving circuit and you just computed the dynamics of the purity, you might be able to get some kind of relatively higher quality, sort of more converged result for this page curve.
I see. So yeah, we did not.
Okay.
Yeah, we did not do that. Yeah. So that no. I just wanted to make one comment about the question on integrable models. So in fact, I have a feeling that even for non-integrable models, so I don't know. I mean, maybe somebody in the audience can. So we are kind of fitting this, but even for non-integral models, you can ask, what about the variance, for example, the variance of the magnetization? So even that could be like a fitting parameter here, right? So it's not just higher integrals of motion. So I know. So from here, I can calculate the energy, magnetization, maybe variance, and technically, even that could be put as something unknown, right? So I mean, so I'm not fully sure that this problem is not just for integral models. Even for non-integral models, there could be some higher corrections here. Yeah. But the belief is anything should improve further. I mean,
You're adding parameters.
Huh?
You're adding parameters to your fit.
Adding parameters, but it's not obvious it will improve. But I think it should improve. Right? So, yeah.
Also, I think for the high entropy initial state, maybe the other conserved quantities are less relevant, right? So that's why you get a better.
Right. For the integral space.
Even the integrals.
Yeah.
Similar to what Takato's talk, right? Where because of some initial conditions, other integrals are kind of irrelevant.
Yeah. Probably that is happening.